The light that reaches your eye from the Andromeda Galaxy began its journey 2.5 million years ago. On Earth, at that time, our distant ancestors were just beginning to shape stone into tools, their minds not yet capable of conceiving the cosmos from which that light originated. That faint smudge of light in the night sky is a time capsule, a message from a past so deep it predates humanity itself. Every star, every distant quasar, is a similar vessel, carrying stories across gulfs of space and time that are almost impossible to comprehend. When we look up, we are not seeing the universe as it is, but as it was, a mosaic of past moments assembled by the finite speed of light. We are archaeologists of photons, piecing together a history from ancient signals that have traveled for eons. But even this vast, backward-looking vista is incomplete. There are horizons we cannot see past, boundaries defined not by distance, but by the very laws that govern reality. One such boundary is woven around an object so dense, so gravitationally dominant, that its escape velocity exceeds the speed of light itself, creating a one-way portal out of our observable universe. Black holes are not holes in the conventional sense. They are destinations. They represent the final, collapsed state of matter, a place where the familiar rules of physics are warped into an unrecognizable form. Their existence, once a purely theoretical prediction from Albert Einstein's general theory of relativity, was a mathematical ghost haunting the equations. Einstein himself was uneasy with the implication that a star could collapse so completely that it would sever itself from the rest of the cosmos, a kind of cosmic self-exile. The idea of such an object dates back even further, to the late 18th century, when the English natural philosopher John Michel and the French mathematician Pierre-Simon Laplace independently reasoned that a body sufficiently massive and compact would have an escape velocity greater than the speed of light, rendering it invisible. For over a century, this concept of a dark star remained a curiosity, a footnote in the history of science. It took Einstein's revolutionary vision of gravity as the curvature of space-time to give it a solid theoretical foundation. Yet, for decades, black holes remained phantoms of mathematics. It was not until 2019 that we captured the first direct image of this ghost's shadow, the silhouette of the supermassive black hole at the center of the galaxy M87, projected against the swirling, superheated gas of its accretion disk. This monumental achievement, produced by the Event Horizon Telescope, a global network of radio telescopes acting as a single, Earth-sized observatory, did not show us the black hole itself, but the boundary of its influence. What we saw was the edge of the abyss, the event horizon, a term that sounds both poetic and final. It is the point of no return. A spaceship could, in theory, orbit a black hole safely, just as planets orbit the sun, but the event horizon is not a physical surface you could touch. It is a demarcation in space-time. Cross it, and your future is no longer your own. Beyond this one-way membrane, the roles of space and time are inverted in a way that defies all human experience. In our familiar universe, we have freedom of movement in 3 spatial dimensions, but are relentlessly carried forward in 1 temporal dimension. We can choose to go left or right, up or down, but we cannot choose to stop moving into the future. Once you cross the event horizon, that freedom vanishes. Time becomes a spatial direction, pointing inevitably toward the center, and space becomes the dimension that flows. Moving forward in time now means moving inexorably toward the singularity, a point of supposedly infinite density and 0 volume where our understanding of physics catastrophically fails. Here, general relativity, the physics of the very large, and quantum mechanics, the physics of the very small, collide in a paradox we cannot yet resolve. This is the ultimate wall, a place where our most successful scientific theories break down, signaling not an end to reality, but an end to our ability to describe it. Some theorists, unwilling to accept an infinity at the heart of nature, propose that the singularity is not a point, but something more complex, a region where quantum gravity effects take over and prevent a total collapse. Perhaps it is a fuzzball, where the information of everything that has fallen in is encoded in a tangled mass of fundamental strings, as suggested by string theory. In this view, a black hole is not an empty void but a solid, albeit exotic, object with no true horizon or singularity. Or perhaps the singularity is a Planck star, an object compressed to the smallest possible size allowed by quantum mechanics, which then rebounds in a big bounce that could create a new universe within the black hole. This idea transforms black holes from cosmic graveyards into potential cosmic wombs, each one a seed for a new reality. Others have speculated about wormholes, theoretical tunnels through space-time that could connect distant parts of our universe or even link to parallel universes. These remain highly speculative, as creating a stable, traversable wormhole would require a form of exotic matter with negative energy, something we have never observed and are not sure can exist. More immediate, and perhaps more testable, is the question of what happens just outside the event horizon. Stephen Hawking's groundbreaking discovery in the 1970s revealed that black holes are not entirely black. Due to quantum effects near the horizon, they radiate particles, a phenomenon now known as Hawking radiation. In the quantum vacuum of empty space, pairs of virtual particles and antiparticles are constantly popping into existence and annihilating each other. Near an event horizon, it is possible for one particle of a pair to fall in while the other escapes. From a distant observer's perspective, it appears as if the black hole is emitting a faint thermal glow. This radiation is incredibly faint for large black holes, but it means they are not eternal prisons. They slowly evaporate, returning their mass and energy to the universe over timescales far longer than the current age of the cosmos. A solar mass black hole would take 10 to the power of 67 years to evaporate, while a supermassive one would take 10 to the power of 100 years. An almost unimaginable stretch of time. This slow leakage of energy raises a profound question known as the information paradox. What happens to the information of the objects that fall in? A fundamental tenet of quantum mechanics is that information can never be destroyed. It can be scrambled, like burning a book. But in principle, one could reconstruct the original information from the final state of the smoke and ash. A black hole, however, seems to erase it completely. When it evaporates, the outgoing Hawking radiation appears to be thermal and random, containing no information about what fell in. Hawking initially believed the information was lost forever, a conclusion that would have required rewriting the foundations of physics. Later, he and other physicists, such as Leonard Susskind and Gerard T. Hooft, proposed that the information might be subtly encoded in the outgoing radiation through quantum correlations, a concept related to the holographic principle, which suggests that all the information contained within a volume of space can be represented on its boundary. Another possibility, the firewall hypothesis, suggests a violent alternative just outside the event horizon. An impenetrable wall of high-energy particles instantly incinerates anything that tries to cross, preserving information on the outside at the cost of violating Einstein's principle of equivalence, which states that falling freely should feel no different from floating in empty space. The debate rages on, because at the heart of this question lies the key to unifying our two great pillars of physics. The gravitational influence of these objects also sculpts time itself. If you were to watch a friend fall toward a black hole from a safe distance, you would witness a strange spectacle. As they approach the event horizon, their time would appear to slow down relative to yours. Their movements would become languid, their signals redshifted to lower and lower frequencies. They would seem to hover at the edge, their image growing dimmer and redder, frozen in time for eternity from your perspective. You would never see them cross, from their perspective. However, time would pass normally. They would cross the event horizon in a finite amount of time, unaware of the moment they pass the point of no return, and continue their journey toward the singularity. This temporal distortion, known as gravitational time dilation, is not just a theoretical curiosity, it is a measurable reality. The clocks on our GPS satellites, orbiting in a slightly weaker gravitational field than we experience on the surface, run faster by about 38 microseconds per day. Without constant correction for this relativistic effect, the entire system would accumulate errors that would render it useless within hours. Black holes come in a variety of sizes, each with a different origin story. Stellar black holes, with masses a few times that of our Sun, are formed from the cataclysmic collapse of massive stars at the end of their lives. When a star more than about 20 times the mass of our Sun exhausts its nuclear fuel, the outward pressure from fusion can no longer support its immense weight, and it collapses catastrophically. The resulting supernova explosion blows the star's outer layers into space, while the core implodes to form a black hole. Intermediate mass black holes, with masses between 100 and 100,000 suns, are a more mysterious class. They are thought to form in the dense cores of globular star clusters through runaway mergers of stars, but their existence is still being actively debated and confirmed. Supermassive black holes, with masses ranging from millions to billions of times that of our Sun, reside at the centers of most large galaxies, including our own Milky Way. The one at our galactic heart, Sagittarius A star, has a mass of about 4 million suns. The origin of these behemoths is still a puzzle. Did they form from the direct collapse of immense gas clouds in the early universe? Or did they grow over billions of years by merging with other black holes and consuming vast quantities of stars and gas? Astronomers have discovered that these giants are not just passive residents of their galaxies, they are active architects. The immense energy released by material falling into a supermassive black hole can power jets of particles that travel at near light speed, blasting out of the galaxy and heating the surrounding intergalactic medium. This process, known as active galactic nucleus feedback, can regulate star formation, preventing the galaxy from growing too large too quickly. In this way, these objects, which represent the ultimate destruction of matter, are also crucial for the creation and evolution of the complex structures we see today. They are a bridge between the physics of the very large and the very small, a laboratory for testing the limits of our knowledge, and a stark reminder that the universe contains boundaries far more absolute than any we have ever encountered on Earth. Our own planet is a sanctuary of predictability and stability, but it is just one world among countless others. In recent decades, we have begun to discover that the universe is teeming with planets, a realization that has transformed our understanding of our place in the cosmos. For millennia, the stars were just points of light, their nature a mystery. The idea that they might be distant suns, with their own orbiting planets, was a philosophical speculation, not a scientific one. That changed in 1995, when astronomers Michel Mayor and Didier Queloz announced the discovery of the first exoplanet orbiting a sun-like star, 51 Pegasi b. This was not a small, rocky world like Earth, but a hot Jupiter, a gas giant orbiting its star in a scorching 4-day period, a type of planet that theory had not predicted. This discovery opened the floodgates. In the years since, thanks to ground-based observatories and dedicated space missions like NASA's Kepler and TESS, the number of confirmed exoplanets has grown to over 5,000, with thousands more candidates awaiting confirmation. We have learned that planets are not rare, they are ubiquitous. There are likely more planets than stars in our galaxy, meaning there are hundreds of billions of them in the Milky Way alone. The methods used to detect these distant worlds are triumphs of ingenuity. The most prolific method is the transit technique, used by Kepler and TESS. It involves staring at a patch of sky and monitoring the brightness of tens of thousands of stars simultaneously. If a planet passes in front of its star from our point of view, it will block a tiny fraction of the starlight, causing a slight periodic dip in the star's brightness. The size of the dip reveals the planet's size, and the time between dips reveals its orbital period. It is like detecting a gnat flying in front of a searchlight from miles away. The radial velocity method, which discovered 51 Pegasi b, looks for the gravitational tug of a planet on its star. As a planet orbits, it causes its star to wobble slightly. This wobble can be detected as a tiny, periodic shift in the star's light, a Doppler effect, similar to the change in pitch of a siren as an ambulance passes by. This method can tell us the planet's mass. By combining these two methods, astronomers can determine a planet's density, giving us our first clues about its composition, whether it is a rocky world, a gas giant, or something in between. The diversity of these newly discovered worlds has shattered our expectations. We have found planets orbiting two stars, so-called circumbinary planets, where one could witness a double sunset reminiscent of the fictional planet Tatooine, we have found super-Earths, rocky planets larger than our own, and mini-Neptunes, gaseous worlds smaller than our ice giants. Two classes of planets that are common in the galaxy but absent from our own solar system. There are planets so close to their stars that their surfaces are molten oceans of lava, and eyeball planets, tidally locked worlds with one side permanently facing their star in perpetual daylight and the other in perpetual frozen night. We have even found rogue planets, worlds that do not orbit any star but wander through the cold, dark expanse of interstellar space, having been ejected from their home systems long ago. The ultimate goal of this search, however, is to find another Earth, a planet that could potentially harbor life. The search focuses on the habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. One of the most promising systems discovered so far is TRAPPIST-1, located about 40 light-years away. It is a tiny, cool red dwarf star orbited by 7 Earth-sized rocky planets. At least 3 of them are located within the habitable zone, raising the tantalizing possibility of worlds with oceans, clouds, and perhaps life. The James Webb Space Telescope is now capable of studying the atmospheres of some of these nearby exoplanets. By analyzing the starlight that passes through a planet's atmosphere during a transit, we can look for the chemical fingerprints of different molecules. We can search for biosignatures, gases like oxygen, methane, and water vapor, which on Earth are produced in large quantities by living organisms. The detection of such a combination of gases in the atmosphere of a distant world would not be definitive proof of life, but it would be the most profound discovery in human history, a sign that we are not alone in this vast, silent universe. It would force us to redraw the boundaries of biology and confront the possibility that the story of life is a cosmic one, not just a terrestrial one. Our instruments, extensions of our senses, peer out into the cosmos and reveal a universe of breathtaking complexity. Yet, for every galaxy we catalog and every star we analyze, we are confronted with the humbling reality that what we see is not the full picture. It is merely a sliver, a luminous foam on the surface of a vast, dark ocean. The very motion of the stars and galaxies tells a story of an invisible presence, a gravitational influence that cannot be accounted for by the matter we can detect. This unseen component, dubbed dark matter, makes up approximately 27% of the universe's mass energy content, outweighing all the ordinary matter of stars, gas, and dust by a factor of more than 5 to 1. It is the silent, invisible giant that holds the cosmos together, the unseen puppeteer pulling the strings of galactic motion. Its existence represents a profound boundary in our perception, a realm of reality that lies beyond the reach of our eyes and telescopes, detectable only through its gravitational shadow. The first whispers of its existence came in the 1930s from the Swiss-American astronomer Fritz Zwicky, a brilliant and famously irascible character. While observing the Coma Cluster, a dense swarm of over 1,000 galaxies, Zwicky noticed something deeply puzzling. He measured the velocities of the individual galaxies and found them to be moving far too quickly. According to the laws of gravity as understood at the time, the visible matter in the cluster, the combined mass of all its stars, was not nearly enough to keep these galaxies gravitationally bound. The cluster should have been flying apart. To solve this puzzle, Zwicky postulated the existence of Dunkel Materiae, or dark matter, an unseen mass providing the extra gravitational glue. His idea was largely ignored for decades, considered too radical a solution for an observational anomaly that might have other explanations. The scientific community was not yet ready to accept that the universe was mostly invisible. The evidence, however, continued to mount, becoming undeniable in the 1970s with the pioneering work of astronomers Vera Rubin and Kent Ford. They meticulously studied the rotation of spiral galaxies, including our own neighbor, Andromeda. They expected to find that stars at the outer edges of a galaxy would orbit more slowly than those closer to the center, just as the outer planets in our solar system move more slowly than the inner ones. Following Kepler's laws, this is because most of the visible mass of a galaxy is concentrated in its central bulge. Instead, they found something completely unexpected. The star's orbital speeds remain surprisingly constant, or even increased, far out from the galactic center. This flat rotation curve was inexplicable unless the galaxy was embedded in a vast, spherical halo of invisible matter, extending far beyond the visible disk of stars. This halo contained the bulk of the galaxy's mass, a silent, gravitational cocoon that governed the motion of the stars within it. Rubin's work provided the smoking gun, transforming dark matter from a fringe idea into a central problem of modern cosmology. Further evidence comes from the phenomenon of gravitational lensing, another prediction of Einstein's general relativity. Massive objects warp the fabric of space-time, causing light from more distant objects to bend around them, much like a lens focuses light. By observing how the light from distant galaxies is distorted as it passes through galaxy clusters, astronomers can map the distribution of mass in those clusters. These maps consistently show that the mass is concentrated not where the visible galaxies are, but in a much larger, smoother distribution of invisible matter. We can see the effect of dark matter's gravity, even if we cannot see the matter itself. It is like inferring the presence of an invisible person by the footprints they leave in the snow. A striking example of this is the bullet cluster, which is actually two galaxy clusters that have passed through each other. The hot gas of the clusters, which contains most of the ordinary matter, collided and slowed down, while the dark matter, which does not interact except through gravity, passed straight through. The result is a clear separation of the visible matter from the gravitational mass, a direct observation of dark matter's ghostly nature. The cosmic microwave background, the afterglow of the Big Bang, also carries the imprint of dark matter. This ancient light, released just 380,000 years after the universe began, is remarkably uniform, but it contains tiny temperature fluctuations. These fluctuations represent the seeds of all future structure, the slight density variations that would eventually grow into the vast galaxies and clusters we see today. However, the fluctuations are too small to have grown into these structures in the 13.8 billion years since the universe began. If only ordinary matter existed, the radiation pressure in the early universe would have prevented ordinary matter from clumping together effectively. Dark matter, being immune to this pressure, could begin to collapse under its own gravity much earlier, forming deep gravitational wells into which ordinary matter could later fall, accelerating the process of structure formation. Without dark matter, the universe today would be a much smoother, more uniform place, devoid of the complex cosmic web that we observe. But what is this mysterious substance? The most straightforward answer, that it is simply ordinary matter that does not shine things like brown dwarfs, cold gas clouds, or rogue planets. Collectively known as machos, has been largely ruled out by observational constraints from gravitational microlensing surveys and Big Bang nucleosynthesis, which places tight limits on the total amount of ordinary or baryonic matter in the universe. The leading candidates are therefore hypothetical subatomic particles that were forged in the heat of the Big Bang and have survived to the present day. These particles would not interact with light or any other form of electromagnetic radiation, which is why they are dark. They would interact only through gravity and possibly the weak nuclear force. The most popular class of candidates is known as WIMPs, or weakly interacting massive particles. These particles would be heavy, perhaps 100 times the mass of a proton, and would be moving relatively slowly, which is why this model is often called cold dark matter. Another promising candidate is the axion, a much lighter, hypothetical particle proposed to solve a problem in the theory of the strong nuclear force called the strong CP problem. If they exist, axions would have been produced in enormous quantities in the early universe, and would form a vast, cold sea of particles, behaving more like a coherent wave than individual particles. Scientists are engaged in a three-pronged search for these elusive particles, a global effort to shine a light on the dark universe. Direct detection experiments are located deep underground, in mines or tunnels like the Sanford Underground Research Facility in South Dakota, or the Gran Sasso National Laboratory in Italy, to shield them from the constant rain of cosmic rays and other background radiation. These experiments use large, ultra-pure detectors made of materials like liquid xenon or germanium crystals, waiting for the vanishingly rare event of a dark matter particle bumping into an atomic nucleus and leaving a tiny, detectable flash of light or heat. So far, despite decades of searching and increasingly sensitive experiments, no definitive signal has been found, leading to what some have called a WIMP-pocalypse, though the search continues to probe for lighter or more weakly interacting particles. Indirect detection experiments search for the products of dark matter annihilation. If two dark matter particles were to collide, they could annihilate each other, producing a shower of more familiar particles, such as gamma rays, neutrinos, or antimatter particles like positrons, which our telescopes could detect. Telescopes like the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer on the International Space Station are scanning the sky for an excess of these signals coming from regions where dark matter is expected to be dense, like the center of our galaxy or nearby dwarf galaxies. Some tantalizing hints have been found, but none have yet risen to the level of a conclusive discovery. Finally, particle colliders like the Large Hadron Collider at CERN are trying to create dark matter particles directly. By smashing protons together at enormous energies, physicists hope to recreate the conditions of the early universe and produce new, undiscovered particles. If a new particle is created that escapes the detector without leaving a trace, it could be a sign of a WIMP or a similar particle being produced and flying away, its presence inferred only by the missing energy and momentum in the collision debris. While the evidence for dark matter is compelling, a minority of physicists advocate for an alternative explanation that our understanding of gravity is incomplete. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in the 1980s, suggests that Newton's law of gravity changes at very low accelerations, such as those experienced by stars in the outer parts of galaxies. This modification would explain the flat rotation curves without the need for dark matter. While MOND has had some remarkable success in explaining the dynamics of individual galaxies using only their visible matter, it has struggled to explain the observations of galaxy clusters and the cosmic microwave background without becoming more complex and less elegant than the standard dark matter model. For now, the dark matter hypothesis remains the dominant paradigm, a placeholder for a profound gap in our knowledge. It is the invisible architecture of the cosmos, the scaffolding upon which the visible universe is built. The quest to identify its nature is one of the most urgent tasks in modern physics, for its discovery would not only solve a cosmological mystery, but could also reveal a whole new sector of particles and forces, a dark realm that mirrors our own, connected only by the gentle, persistent pull of gravity. But dark matter is not the only invisible component dominating the cosmic inventory. An even more mysterious substance is pushing the universe apart, shaping its ultimate destiny. The cosmic stage is not static. Since the moment of its birth, the universe has been expanding, a discovery made by Edwin Hubble in the 1920s that reshaped our understanding of our place in cosmic history. For most of the 20th century, the prevailing question was whether this expansion would continue forever or if the mutual gravitational attraction of all the matter in the universe would eventually slow it down, halt it, and perhaps even reverse it into a cosmic collapse, a big crunch. The fate of the universe seemed to hang in the balance, a cosmic battle between the outward momentum of the Big Bang and the inward pull of gravity. The answer, when it came, was one of the most surprising in the history of science. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were studying distant type Ia supernovae, a type of stellar explosion that serves as a reliable standard candle for measuring cosmic distances to precisely measure the rate at which the expansion was slowing down. But they found the opposite. The distant supernovae were dimmer and therefore farther away than they should have been. The expansion of the universe is not slowing down, it is accelerating. This was a revelation that turned cosmology on its head, earning its discoverers the Nobel Prize in Physics in 2011. To explain this accelerated expansion, there must be some form of energy inherent in the fabric of space itself, a repulsive force that is pushing the universe apart, acting in opposition to gravity. This mysterious component was named dark energy, and according to our best current measurements, it constitutes about 68% of the total energy density of the universe. It is the dominant force in the cosmos today, yet its nature remains one of the deepest mysteries in all of science. It is not matter. It is not radiation. It seems to be a property of the vacuum, an intrinsic energy of empty space. Its existence defines a new kind of cosmic boundary, a horizon beyond which information can never reach us, created by the accelerating expansion of space-time itself. One of the leading explanations for dark energy is the cosmological constant, an idea that Albert Einstein originally introduced into his equations of general relativity in 1917. He added it to counteract the pull of gravity and achieve a static, unchanging universe, which was the prevailing belief at the time. When Hubble discovered the expansion of the universe, Einstein famously discarded the cosmological constant, calling it his biggest blunder. The irony is that his blunder may have turned out to be his most prophetic insight. If dark energy is indeed the cosmological constant, represented by the Greek letter lambda, it means that every cubic centimeter of empty space contains a small, fixed amount of this repulsive energy. As the universe expands, more space is created, and with it, more dark energy, which in turn drives the expansion to accelerate even faster. This creates a feedback loop, a runaway expansion that will shape the ultimate destiny of the cosmos. The consequences of this accelerating expansion are profound and somewhat melancholic. In the distant future, perhaps 100 billion years from now, all galaxies outside our own local group, the small cluster of galaxies that includes the Milky Way and Andromeda, will have been pushed so far away by the expansion of space that their light will no longer be able to reach us. The space between us and them will be stretching faster than the speed of light. For a future observer in our galaxy, the night sky will be a dark and lonely place. The rich tapestry of distant galaxies will have vanished beyond a cosmic horizon, leaving only the stars of the Milky Way and its immediate neighbors, which will have by then merged into a single, large elliptical galaxy. Future astronomers would have no way of knowing that other galaxies exist, or that the universe began with a Big Bang. The evidence for these fundamental truths would be lost forever, carried away by the relentless expansion of space. It is a sobering thought that our current moment in cosmic history may be a uniquely privileged one, a time when the universe is old enough to have formed complex structures, but young enough that the evidence of its origins is still visible. Alternative theories for dark energy exist, though they are less favored. One is the idea of quintessence, a dynamic field that fills space, similar to the cosmological constant, but with an energy density that can change over time. Depending on how this field evolves, the acceleration of the universe could slow down, stop, or even become more extreme in the future. Another possibility is that general relativity itself needs to be modified on the largest cosmic scales. Just as Mondi proposes to modify gravity on galactic scales, perhaps the observed acceleration is not due to a new form of energy, but is a manifestation of a more complex gravitational theory than Einstein's. The most tantalizing connection, however, is with the quantum world. Quantum field theory predicts that the vacuum should be teeming with virtual particles, creating a vacuum energy that has properties very similar to the cosmological constant. The problem is that when physicists try to calculate the expected amount of this vacuum energy, the result is catastrophically wrong. The theoretical prediction is about 10 to the power of 120 times larger than the observed value of dark energy. This discrepancy, known as the cosmological constant problem, has been called the worst theoretical prediction in the history of physics. It suggests a profound misunderstanding in our connection between the quantum world and the cosmos at large. Dark matter and dark energy together constitute 95% of the universe. All of our physics, all of our experience is based on the remaining 5% of ordinary matter. We are like explorers who have landed on a new continent and, having studied a single beach, believe we understand the entire landmass. The rest lies hidden, its nature and properties a mystery. Dark matter acts as the universe's sculptor, its gravitational pull gathering matter into the cosmic web of galaxies and clusters. Dark energy acts as the universe's accelerator, its repulsive force driving everything apart. It is a grand cosmic struggle, a tug-of-war between attraction and repulsion that will determine the ultimate fate of the universe. If dark energy is the cosmological constant and remains constant, the universe is heading toward a big freeze or heat death. It will continue to expand and cool indefinitely. Stars will burn out, black holes will evaporate, and the cosmos will become a cold, dark, and empty place. A diffuse soup of elementary particles at a temperature infinitesimally close to absolute zero. If dark energy's strength increases over time, a more violent end known as the Big Rip could occur. The accelerating expansion would become so powerful that it would eventually overcome not just the gravity holding galaxies and stars together, but the electromagnetic and nuclear forces holding atoms and even atomic nuclei together. The entire fabric of reality would be torn apart. The quest to understand these dark components is therefore not just an academic exercise. It is a quest to understand the fundamental nature of our reality and its ultimate destiny. It is a journey into an invisible landscape that shapes everything we see, a reminder that the universe is far stranger and more mysterious than we could ever have imagined from our small, brightly lit corner of it. The familiar flow of time, a river carrying us from a fixed past to an open future, is a deeply ingrained human intuition. It seems to govern our lives with an absolute, unyielding consistency, a universal clock ticking away the moments of existence. Yet, at the dawn of the 20th century, Albert Einstein dismantled this intuition with his special and general theories of relativity. He showed that time is not an absolute metronome ticking at the same rate for everyone in the universe. Instead, it is a malleable, relative quantity, woven together with space into a single, dynamic fabric called spacetime. Time can be stretched and compressed, its passage dependent on an observer's motion and the strength of the gravitational field they inhabit. This shattering of the absolute nature of time represents a crossing of a profound conceptual boundary, from the classical world of Newton to the strange, relativistic cosmos we now know we inhabit. The phenomenon of time dilation, a core prediction of special relativity, states that for a moving observer, time passes more slowly than for a stationary one. The faster you move through space, the slower you move through time. If one of a pair of identical twins were to embark on a journey through space at a velocity approaching the speed of light, say 99.9% of it, upon their return to Earth after what felt like 5 years to them, they would find that over a century had passed for their stay-at-home sibling. The traveling twin would be biologically younger. This is not science fiction, it is a confirmed physical reality, demonstrated countless times with atomic clocks on airplanes, rockets, and satellites. It is the reason that time travel to the future is, in principle, physically possible. Gravity, according to general relativity, also warps time. The stronger the gravitational field, the slower time flows. A clock at sea level will tick slightly more slowly than a clock on a mountaintop, where the Earth's gravity is marginally weaker. This effect becomes extreme near massive objects. If you could hover near the surface of a neutron star, a city-sized remnant of a collapsed star with a mass greater than our sun, for every hour that passed for you, years or even decades could pass for a distant observer. At the event horizon of a black hole, this effect reaches its limit. From the perspective of the outside universe, time for an object at the horizon effectively stops. This malleability of time opens up the theoretical possibility of one-way travel into the future. By traveling at relativistic speeds or spending time in a strong gravitational field, one could jump forward in time relative to the rest of the universe. Travel to the past, however, is a far more problematic concept, fraught with paradoxes and theoretical hurdles. While Einstein's equations do not explicitly forbid it, they suggest that it would require exotic physical constructs that may be impossible to create. One such construct is a wormhole or an Einstein-Rosen bridge, which could theoretically act as a shortcut between two different points in space-time. If the two mouths of a wormhole were manipulated in a specific way, one kept stationary and the other taken on a high-speed journey, it could become a time machine, allowing travel between the two different moments in time to which the mouths are connected. Another theoretical possibility involves infinitely long, rotating cylinders, known as Tipler cylinders, which could drag space-time around them so violently that they create closed time-like curves, pathways that loop back on themselves in time. However, both of these scenarios would likely require vast amounts of negative energy to stabilize, and many physicists believe that the laws of nature may conspire to prevent their formation. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics themselves, perhaps through yet unknown quantum gravity effects, prevent the creation of time machines on a macroscopic scale. This would protect the universe from the logical contradictions that could arise from backwards time travel, such as the famous grandfather paradox, where a traveler goes back in time and prevents their own grandfather from meeting their grandmother, thus preventing their own birth and their ability to travel back in time in the first place. From a quantum perspective, time becomes even stranger, and the boundary between past, present, and future begins to blur. The world of quantum mechanics is one of probabilities and uncertainties, where particles can exist in multiple states at once, in a state of superposition, until they are measured. In some experiments, like the delayed choice quantum eraser, it appears as if a choice made in the present can retroactively influence an event that has already happened in the past. This does not mean we can send information back in time, but it does suggest that the relationship between cause and effect at the quantum level is not as straightforward as it is in our classical world. The phenomenon of quantum entanglement, which Einstein called spooky action at a distance, further complicates our notion of time and space. When two particles are entangled, their fates are linked, no matter how far apart they are. If you measure a property of one particle, you instantly know the corresponding property of the other. Faster than light could travel between them. This seems to violate the principle of locality, but it does not allow for faster than light communication. It simply reveals a deep, non-local connection that is a fundamental feature of reality. These quantum mysteries have led some physicists to speculate about the very nature of time itself. John Wheeler's participatory anthropic principle suggests that the universe, in a sense, comes into being through the act of observation. In this view, observers are not passive witnesses but active participants in the creation of reality, and the past of the universe may not be fully fixed until it is observed. Other interpretations, like the many worlds interpretation, suggest that every quantum measurement causes the universe to split into multiple branches, with each possible outcome realized in a separate, parallel universe. In this framework, all possible histories are real, and the arrow of time as we perceive it is just the path we happen to be following through one branch of this vast, ever-splitting tree of realities. There are even more radical ideas that propose time may not be a fundamental aspect of reality at all. In some approaches to quantum gravity, such as loop quantum gravity, space-time is not a smooth, continuous fabric, but is made of discrete, indivisible units, or quanta of space and time. At the Planck scale, at this most fundamental level, the concept of a smooth flow of time may dissolve. Instead, time might be an emergent phenomenon, a statistical effect that arises from the more fundamental interactions of these quantum units. Much like temperature is not a property of a single molecule, but an emergent property of the average motion of many molecules. In this view, our perception of a flowing river of time would be an illusion, a macroscopic approximation of a more complex, timeless quantum reality. The universe would be a static block of space-time, where the past, present, and future all exist simultaneously, and our consciousness simply moves through this block, creating the illusion of passage. This idea, known as eternalism, has profound philosophical implications, suggesting that all moments are equally real. This brings us to the very concept of nothingness. Our intuition tells us that empty space is a void, a state of absolute nothing. But quantum field theory reveals that what we call the vacuum is far from empty. It is a seething cauldron of activity, a quantum foam where virtual particles and antiparticles constantly pop into and out of existence, borrowing energy from the vacuum for fleeting moments, as allowed by Heisenberg's uncertainty principle. This zero-point energy of the vacuum is real and has measurable effects, such as the Casimir effect, where two uncharged metal plates placed very close together in a vacuum are pushed together by the pressure of the virtual particles outside them, being greater than the pressure between them. This invisible's energetic sea is the true ground state of reality, the baseline upon which all matter and energy exist. It may even be the source of everything. Some cosmological models, like those proposed by Lawrence Krauss and Alexander Vilenkin, suggest that our entire universe could have arisen as a quantum fluctuation in this pre-existing vacuum. A universe from nothing, though this nothing is a far cry from the philosophical concept of absolute non-existence. It is a nothingness filled with potential. The quantum vacuum is the ultimate boundary, the interface between existence and non-existence, and it may hold the key to understanding the origin of the universe. The constant roiling fluctuations in the vacuum in the universe's first moments are thought to have been stretched to cosmological scales by the process of inflation, becoming the seeds for the large-scale structure of galaxies and clusters we see today. The faint temperature variations in the cosmic microwave background are a direct snapshot of these quantum jitters, writ large across the sky. So, the largest structures in the universe may have their origins in the smallest, most ephemeral quantum fluctuations in the void, whether time is a fundamental river, a branching tree, a static block, or an emergent illusion. Its true nature remains one of the deepest and most personal mysteries of the cosmos. It is the canvas on which our lives are painted, yet its secrets are woven into the very fabric of reality. From the quantum foam at the smallest scales to the expanding horizons of the universe at the largest. Understanding time is not just a challenge for physics. It is a journey into the heart of what it means to exist, and it forces us to confront the possibility that our entire reality is just one of many, a single story in an infinite cosmic library. The notion that our universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, might not be the only one, is an idea that has migrated from the realm of science fiction and philosophy into the frontiers of theoretical physics. The concept of the multiverse is not a single, coherent theory, but a collection of different models, each arising from a different area of physics, and each proposing a different kind of parallel reality. It pushes the boundary of our cosmic context to its ultimate limit, suggesting that our entire universe is but a single component in a far grander, and perhaps infinite, structure. The implications of this are staggering, forcing us to reevaluate not only our place in the cosmos, but the very uniqueness of our existence and the physical laws that govern it. One of the most compelling arguments for a multiverse comes from the theory of cosmic inflation. Inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential, superluminal expansion, driven by a quantum field called the inflation field. It stretched from a size smaller than an atom to a size larger than a galaxy in an instant. This theory elegantly explains several key features of our universe, such as its large-scale uniformity and its flat geometry. In many models of inflation, developed by physicists like Andrei Linde and Alan Guth, this process, once started, is eternal. While inflation may have ended in our pocket of space-time, creating our observable universe, it continues in other regions, constantly spawning new bubble universes, each with its own Big Bang, like bubbles forming in a pot of boiling water. New universes would constantly nucleate out of the eternally inflating background. These other bubble universes could be vastly different from our own. The properties of each universe would depend on how the inflation field settled down into its low-energy state. This could lead to universes with different physical constants, different numbers of spatial dimensions, and even different fundamental particles and forces. Most of these universes would likely be sterile and uninhabitable, perhaps collapsing back on themselves moments after they form, or expanding so rapidly that no structures could ever coalesce. Our universe, with its seemingly fine-tuned laws, would be one of the rare, successful bubbles where conditions were right for complexity and life to emerge. This Level 2 multiverse provides a naturalistic explanation for the fine-tuning problem, but it comes at the cost of postulating an infinite number of unobservable other worlds. A second type of multiverse arises from the strange rules of quantum mechanics. The many worlds interpretation, proposed by Hugh Everett in the 1950s as his PhD thesis, offers a radical solution to the measurement problem in quantum physics. In the standard Copenhagen interpretation, a quantum system exists in a superposition of all possible states until it is measured, at which point its wave function collapses into a single, definite state. Everett found this collapse to be an arbitrary and unnecessary addition to the underlying mathematics of quantum theory. He suggested that the collapse never happens. Instead, all possible outcomes of a quantum event actually occur, each in its own separate universe. Every time a quantum choice is made, whether a radioactive atom decays or not, whether a particle passes through the left slit or the right reality splits. In this level 3 multiverse, there is an incomprehensibly vast, constantly branching tree of parallel realities. In one universe, you are reading this sentence. In another, you looked away a moment ago. In one, the dinosaurs were never wiped out by an asteroid. In another, humanity has already colonized the stars. All of these universes would be equally real, existing simultaneously in a different part of a vast, abstract mathematical space known as Hilbert space. We would have no way of interacting with them, as they are decoherent from our own world. The many worlds interpretation is elegant in its mathematical simplicity, as it requires no extra ad hoc postulates like wave function collapse. But it is ontologically extravagant, requiring the existence of a near infinite number of parallel versions of ourselves and our world. A third possibility for a multiverse comes from string theory, the leading candidate for a unified theory of everything that reconciles general relativity and quantum mechanics. String theory posits that the fundamental constituents of reality are not point-like particles but tiny, one-dimensional vibrating strings. For the theory to be mathematically consistent, it requires the existence of extra spatial dimensions. Beyond the 3, we experience typically 6 or 7 of them. These extra dimensions are thought to be curled up or compactified on a scale too small for us to detect. The geometry of these extra dimensions, the shape of the so-called Calabi-Yau manifolds, determines the vibrational modes of the strings, which in turn determine the properties of the particles and forces in our universe. The problem is that string theory does not predict a unique way for these extra dimensions to be curled up. Instead, it allows for a vast number of possible solutions, perhaps as many as 10 to the power of 500. Each of these solutions corresponds to a different vacuum state, a different set of physical laws and constants. This collection of all possible universes is known as the string theory landscape. Our universe would be just one of these many possible worlds. In a related concept from M-theory, an extension of string theory, our universe could be a three-dimensional brain floating in a higher dimensional space, or bulk. There could be other brains, other universes, floating parallel to our own in this higher dimensional reality. These brain worlds could be just millimeters away from us in the extra dimensions, but we would be unable to perceive them because our matter and light are confined to our own brain. Gravity, however, might be able to leak between the brains, which could explain why gravity is so much weaker than the other fundamental forces. In some models, the Big Bang itself could have been caused by the collision of two such brains. A fourth, and perhaps the most straightforward, type of multiverse is simply a consequence of an infinite universe. Our observable universe is the region of space from which light has had time to reach us since the Big Bang, a sphere about 93 billion light-years in diameter. But there is no reason to believe that the universe ends at this horizon. If space is spatially infinite, as current observations suggest, and the distribution of matter and energy is roughly uniform on the largest scales, then in that infinite space, every possible configuration of particles within a finite volume must eventually repeat far beyond our observable horizon. There would be other regions of space identical to our own. In this level 1, or quilted multiverse, there would be an infinite number of regions the size of our observable universe. And in some of them, the arrangement of matter would be exactly the same as it is here. Somewhere out there, there would be another Earth, with another version of you, living a life identical to yours. And there would be other regions where things are almost identical, but with one tiny difference. This is not a different set of physical laws, but simply a consequence of infinite space and finite possibilities. The existence of a multiverse, in any of these forms, could offer a neat explanation for the apparent fine-tuning of our universe. The fundamental constants of nature, the strength of gravity, the mass of the electron, the value of the cosmological constant seem to be precisely dialed in to the narrow range that allows for the formation of complex structures like stars, planets, and life. If these values were even slightly different, the universe would be a sterile, empty place. This fine-tuning has led some to argue for a divine creator, The multiverse provides a naturalistic alternative if there are an infinite number of universes, each with a random set of physical constants. Then it is no surprise that we find ourselves in one of the rare universes where the conditions are right for our existence. We are here because we could not be anywhere else. This is the anthropic principle in its strongest form. While the concept of a multiverse is tantalizing, it remains on the very edge of science, blurring the line with metaphysics. By definition, these other universes are likely to be forever beyond our ability to directly observe. This has led to a fierce debate about whether the multiverse is a scientific theory at all, as a theory should be falsifiable. Proponents argue that it is a natural consequence of our best current theories, like inflation and string theory, and that we should follow the mathematics where it leads. They also point to potential, indirect ways to test these ideas. The collision of our bubble universe with another in the distant past could have left a detectable signature, a bruise in the cosmic microwave background. The detection of extra dimensions or specific particles predicted by string theory at the Large Hadron Collider could lend support to the brain world scenario. For now, the multiverse remains a deeply compelling but unproven idea, a grand and humbling vision of a reality far vaster than our ancestors, or even the scientists of a century ago, could ever have dreamed. It suggests that our entire cosmos, in all its unimaginable scale and complexity, may be just a single grain of sand on an infinite cosmic shore, one story among an infinity of others, all playing out across the boundless landscape of reality. At the end of our cosmic journey, after crossing the boundaries of observation, perception, and reality itself, we are left to confront the final frontiers, the boundary of the future, and the boundary of meaning. Having contemplated the possibility of infinite worlds, we return to our own, to the singular story of our universe, and ask the ultimate questions. What is its final chapter, and what is our role in its unfolding narrative? The story of the universe is one of constant transformation, from the fiery birth of the Big Bang to the intricate dance of galaxies we see today. But all stories have an end, and the laws of physics, particularly the second law of thermodynamics, suggest that our universe is no exception. The second law of thermodynamics states that in a closed system, entropy, a measure of disorder or randomness, always increases. The universe, as a whole, appears to be a closed system, and so it is relentlessly marching toward a state of maximum entropy, a final, uniform equilibrium. The discovery of dark energy and the accelerating expansion of the universe has given us a clearer, though more desolate, picture of what this end might look like. If dark energy is a cosmological constant, the prevailing scenario for the universe's ultimate fate is the Big Freeze, or heat death. The timeline for this future is mind-bogglingly vast. In about 4.5 billion years, our Milky Way galaxy will collide and merge with the Andromeda galaxy, forming a new, larger elliptical galaxy, which some have dubbed Milkomeda. This will be a spectacular, but not particularly destructive, event for individual stars. In about 100 billion years, the accelerating expansion will have carried all other galaxies beyond our cosmic horizon, leaving Milkomeda as a solitary island in an endless, empty void. Over the next trillions of years, the process of star formation will cease as the last reserves of interstellar gas are exhausted. The existing stars will one by one burn out. The longest-lived stars, the small, cool red dwarfs, will continue to shine for up to 100 trillion years, but they too will eventually flicker out, becoming cold, dark black dwarfs. The universe will enter its degenerate era, populated only by the dead remnants of stars, black dwarfs, neutron stars, and black holes. Even these remnants are not eternal. Over timescales so long they defy description, 10 to the power of 40 years or more, protons themselves may decay, causing the dead stars and planets to dissolve into a bath of radiation and lighter particles. The only remaining objects of significance will be black holes, but they too will succumb to entropy. Through Hawking radiation, they will slowly evaporate, their mass converted back into energy. The process will be agonizingly slow, but inevitable. The last supermassive black holes will finally disappear after perhaps 10 to the power of 100 years, leaving behind a universe that is a cold, dark, and unimaginably dilute soup of photons, neutrinos, and other elementary particles, all at a temperature infinitesimally close to absolute zero. This is the ultimate state of equilibrium, the heat death of the universe, a future of eternal, unchanging darkness. But what if dark energy is not constant, if its repulsive force were to grow stronger over time, a more violent end? The Big Rip could await us. In this scenario, the accelerating expansion would become so powerful that in the final moments of the universe, it would overcome all other forces. First, it would tear apart clusters of galaxies, then the galaxies themselves. In the final minutes, it would overcome the gravity holding stars and planets together. In the final fractions of a second, it would overwhelm the electromagnetic force, ripping atoms apart. Finally, it would tear apart atomic nuclei themselves, reducing the entire universe to a sea of unbound elementary particles. A less likely, but still possible, scenario is the Big Crunch. If dark energy were to reverse its character and become attractive, the expansion of the universe could slow, halt, and reverse. The universe would begin to contract, heading toward a fiery end as everything collapses back into a singularity, a mirror image of the Big Bang. Some theories, like loop quantum gravity, suggest that this crunch could lead to a big bounce, giving birth to a new, expanding universe in an eternal cycle of creation and destruction. In the face of these immense, impersonal cosmic fates, it is natural to ask about the fate of life and intelligence. If we are the only intelligent species in our galaxy, or even our observable universe, a question arises why. This is the heart of the Fermi paradox. The universe is ancient and vast. There has been ample time for other technological civilizations to arise and spread throughout the galaxy. Yet, we see no evidence of them, no megastructures, no interstellar communications, no signs of cosmic engineering. Where is everybody? One possible answer is the Great Filter, the idea that there is some evolutionary or technological hurdle that is extremely difficult for life to overcome. This filter could be in our past, meaning that the emergence of life, or complex life, or intelligence, is an incredibly rare event, making us one of the first, or only, civilizations to exist. Or, more ominously, the Great Filter could be in our future. Perhaps all advanced civilizations inevitably destroy themselves through nuclear war, environmental collapse, or the creation of uncontrollable artificial intelligence. Or perhaps there is some natural cosmic threat that inevitably wipes them out. In this case, the silence of the cosmos would be a warning. Other solutions to the paradox are less dramatic. Perhaps interstellar travel is simply too difficult and expensive for any civilization to pursue on a large scale. Perhaps they are out there, but they are deliberately hiding from us, observing us as if we are in a cosmic zoo or nature preserve, a hypothesis known as the zoo hypothesis. Or perhaps their biology and technology are so different from our own that we would not even recognize their signals or their presence. They could be living in the interiors of stars, or as vast, distributed intelligences in the cold of interstellar space. The silence of the universe remains one of the most profound and unsettling mysteries, a mirror reflecting our own hopes and fears for the future of humanity. This brings us back to ourselves, to this brief, flickering moment of consciousness on a small, rocky planet, faced with the vastness of cosmic time and the apparent indifference of the universe. What is our place for millennia? We believed we were the center of creation. Science has shown us that we are not the physical center of anything. We live on an unremarkable planet, orbiting an average star, in a typical galaxy, in a possibly infinite sea of other universes. This can be seen as a cosmic demotion, a story of our ever-dwindling significance. But there is another perspective. We are, as far as we know, the only beings in the universe capable of understanding its laws, appreciating its patterns, and asking these questions. We are made of stardust, the ashes of long-dead stars, the carbon in our cells, the oxygen we breathe, the iron in our blood, all were forged in the hearts of stellar furnaces and scattered across the galaxy by supernova explosions. We are not separate from the cosmos, we are a part of it. We are the universe made conscious. In the words of Carl Sagan, We are a way for the cosmos to know itself. This idea bestows upon us a unique and profound responsibility. In a universe that may be largely devoid of meaning, it is our consciousness that creates it. We are the storytellers, the artists, the lovers, the scientists. We are the ones who look up at the silent, starry sky and see not just points of light, but the history of the universe and the potential for the future. We are the ones who care. The physicist Richard Feynman once compared science to being a child in a vast library, where all the books are written in a language we do not understand. We slowly, painstakingly, decipher the alphabet, the grammar, the syntax, and begin to read the stories that nature has written. This image captures the essence of our quest for knowledge. It is a quest born of humility, curiosity, and a sense of wonder. At the end of our journey, we are left with more questions than answers. The boundaries of our knowledge have expanded, but so has the shoreline of our ignorance. But perhaps it is in the questions themselves, in our insatiable desire to understand, that our true significance lies. The next time you look up at the night sky, remember that you are not just an observer of the cosmos, but an integral part of it, in your eyes, which observe the stars. The universe is looking at itself and contemplating its own existence. In that moment of connection, in that flash of self-awareness, the infinitely large meets the infinitely small, the objective universe meets the subjective mind, and the great cosmic story finds its voice.
Imagine a place of perfect darkness, a silence so profound that it contains no echo, a void so complete that it holds no matter. For millennia, this was our image of space, our definition of nothingness. But this quiet emptiness is an illusion. It is the greatest secret of the cosmos, a secret that modern physics has only just begun to unveil. What we perceive as empty space is not empty at all. It is a seething, vibrant, and powerful quantum sea, an invisible ocean of energy that permeates every corner of the universe. This is the quantum vacuum, and it is the true foundation of our reality. It is a stage where the laws of our classical, intuitive world break down, and a stranger, more fundamental set of rules takes over. On this stage, particles can be in multiple places at once. They can be connected across vast, cosmic distances in an instant. They can tunnel through barriers that should be impenetrable. This is a reality where the very act of looking at something changes what is there. The quantum vacuum is not a passive backdrop. It is an active, creative medium, a silent but powerful engine that shapes the destiny of the universe. It is a place where matter, energy, and even time itself are born from the incessant, ghostly dance of quantum fields. Today, we will step behind the curtain of classical reality. We will part the veil of the visible, and we will journey into the heart of this mysterious, invisible realm. We will explore the paradoxes, the puzzles, and the profound philosophical implications of a universe where the most potent force may be the energy of emptiness itself. This is a journey that will challenge your perceptions, your assumptions, and your very understanding of what it means to exist. Because in the quantum world, reality is far stranger, more flexible, and more beautiful than you can possibly imagine. One of the first and most unsettling signposts on the road into this quantum territory is a thought experiment involving a cat, a box, and a single, unpredictable atom. It is the story of Schrödinger's cat, a parable designed not to describe a real experiment, but to expose the jarring and seemingly absurd consequences of applying the laws of quantum mechanics to the macroscopic world we inhabit. Inside a sealed box, a cat's life hangs in the balance, its fate linked to the decay of a single radioactive atom. If the atom decays, a mechanism is triggered, a vial of poison is shattered, and the cat dies. If the atom does not decay, the cat lives on. From our classical perspective, The situation is simple. The cat is either alive or dead. We just don't know which until we open the box. But quantum mechanics offers a far more radical and disturbing picture. A radioactive atom, until it is measured, exists in a state of superposition. It has both decayed and not decayed at the same time. And because the cat's fate is quantum mechanically entangled with the atoms, the cat itself must also be in a superposition of states. It is, in the bizarre and unsettling language of the quantum world, simultaneously alive and dead, a ghostly amalgamation of two mutually exclusive realities, coexisting within the unobserved confines of the box. This is not a statement about our ignorance. It is a statement about the fundamental nature of unobserved reality. The cat's reality is not a single definite state, but a wave function, a cloud of probabilities. The moment we open the box, the moment our observation interacts with the system, this wave function collapses. The superposition is broken, and a single definite reality is chosen from the menu of possibilities. The cat is either alive or it is dead. The act of looking seems to have forced the universe to make up its mind. This measurement problem is the deep, unresolved wound at the heart of quantum mechanics. It raises profound questions about the nature of reality and the role of the observer. Does the world have definite properties when we are not looking, or does the act of observation itself bring the world into being? Schrödinger's cat is a macroscopic amplifier of this quantum weirdness, a bridge from the abstract world of particles to the concrete world of our experience. It is a metaphor for the inherent uncertainty and potentiality that underlies all of existence. We are all, in a sense, living in Schrödinger's box, our own futures existing as a superposition of all possible outcomes until the moment of now collapses the wave function of our own lives. And as we drift into the liminal space of sleep, our own consciousness enters a state akin to that of the unobserved cat. The definite classical reality of the waking world fades, and we are suspended in a superposition of memories, thoughts, and dreams, a state where life and death, past and future, self and other, can coexist in a fluid, paradoxical, and deeply creative dance. The bizarre state of Schrödinger's cat is a direct consequence of the principle of quantum superposition, a cornerstone of the quantum worldview that shatters our classical intuition about how things exist in the world. In our everyday experience, an object has a single, definite set of properties. A ball is here, not there. A car is red, not blue. But at the fundamental, subatomic level, the rules are different. A quantum particle, like an electron, is not a solid, point-like object. It is better described as a probability wave, a diffuse cloud of potential that is spread out over a region of space. Before it is measured, it does not have a definite position. It exists in a superposition of all possible positions. It is, in a very real sense, in many places at once. The most striking and famous demonstration of this is the double-slit experiment, when a beam of electrons is fired at a barrier with two parallel slits, and we do not try to determine which slit each electron passes through. An interference pattern appears on a detector screen behind the barrier. This pattern of alternating bright and dark bands is the classic signature of waves interfering with each other, like the ripples from two stones dropped in a pond. This happens even if the electrons are fired one at a time. Each individual electron seems to pass through both slits simultaneously, as a wave, and then interfere with itself. It is a mind-bending result that suggests that the electron's reality is not localized until it is forced to be. The moment we place a detector at one of the slits to watch which path the electron takes, the wave-like behavior vanishes. The interference pattern disappears, and we see two simple bands on the screen, corresponding to the two slits. The electron now behaves like a well-behaved particle, choosing one path or the other. The act of measurement, of gaining which path information, has collapsed the superposition and forced the electron to adopt a single, definite reality. Superposition is not just a theoretical curiosity, it is the engine of quantum technologies. A classical computer bit is binary. It can be either a 0 or a 1. A quantum bit, or qubit, can be in a superposition of both 0 and 1 at the same time by linking many qubits together. A quantum computer can explore a vast computational space simultaneously, giving it the potential to solve problems that are far beyond the reach of any classical machine. But the implications of superposition extend beyond technology and into the very fabric of our subjective experience. The state of our own mind often resembles a superposition. We can hold contradictory feelings at the same time, love and frustration, hope and fear. Our identity is not a single, fixed thing, but a superposition of our various roles, memories, and potential selves. And in the state of sleep, this mental superposition becomes the dominant reality. The linear, logical, and collapsed state of waking consciousness gives way to the fluid, associative, and superpositional nature of the dream world. In a dream, we can be both the protagonist and an observer. We can be in our childhood home and a futuristic city at the same time. The rigid either-or logic of the classical world is replaced by the inclusive both-and logic of the quantum realm. Superposition is the universe's way of telling us that reality, at its core, is not a collection of fixed facts, but a vibrant, dynamic, and multi-layered web of possibilities. And every night, as we surrender to sleep, we are given the chance to immerse ourselves in this fundamental, creative, and endlessly mysterious aspect of our own being. The transition from the probabilistic, superpositional world of quantum potential to the definite, singular world of classical reality is the central mystery of the quantum measurement problem. The wave function is the mathematical description of a quantum system's superposition, a complete catalog of all its possibilities and their associated probabilities. As long as the system is isolated, its wave function evolves in a smooth, continuous, and perfectly deterministic way, governed by the elegant Schrodinger equation. But the moment a measurement occurs, this smooth evolution is violently interrupted. The wave function is said to collapse, and from the vast menu of possibilities, a single random outcome is actualized. This collapse is not part of the Schrodinger equation. It is a separate, mysterious process that we have to add to the theory to make it work. But what, precisely, constitutes a measurement? Is it the interaction with a large classical measuring device? Is it the irreversible recording of information, or does it require the intervention of a conscious observer? This is the question that has spawned a century of debate and a zoo of different interpretations of quantum mechanics. The traditional Copenhagen interpretation, championed by Niels Bohr, takes a pragmatic but philosophically unsatisfying stance. It simply posits a fundamental divide, a shifty split, between the quantum world of microscopic systems and the classical world of our measuring apparatus. When these two worlds interact, a collapse occurs. The theory does not explain the mechanism of this collapse. It treats it as a primitive, unexplained feature of nature. This reluctance to address the how of the collapse led many physicists to seek alternatives. The many worlds interpretation of Hugh Everett III offers a breathtakingly bold solution. The collapse never happens. The wave function is the complete description of reality, and its smooth evolution is the only process that ever occurs. When a measurement is made, the universe itself branches into multiple, parallel realities, one for each possible outcome. In one world, the electron goes through the left slit. In another, it goes through the right. The observer also splits, with different versions of the observer experiencing different outcomes. In this view, reality is a constantly branching tree of possibilities, and we are just following one particular path through this vast multiverse. There is no special measurement process, no mysterious collapse, only the universal, deterministic evolution of the wave function of the whole cosmos. A different approach is taken by objective collapse theories. These models propose that the collapse is a real, physical process that happens spontaneously, independent of any observer. The collapse is a random, probabilistic event, and its likelihood depends on the size and complexity of the system. For a single, isolated particle, the chance of a spontaneous collapse is infinitesimally small, so it can maintain its superposition for a long time. But for a macroscopic object like a cat or a measuring device, which consists of trillions upon trillions of entangled particles, the probability of a collapse occurring in one of its constituent particles becomes overwhelmingly high, triggering a rapid chain reaction collapse of the entire system. This is why we never see macroscopic superpositions. They are simply too fragile, collapsing into a definite state in an immeasurably short time. The measurement problem remains the most profound conceptual challenge in modern physics. It is the point where our theories of the physical world seem to touch upon the nature of information, reality, and perhaps even consciousness itself. And it is a problem that finds a powerful experiential parallel in the nightly journey of our own minds. As we fall asleep, the constant bombardment of sensory information from the external world, the stream of measurements that keeps our waking consciousness collapsed into a single, coherent reality, begins to cease. The neural gateways to the environment close, and our consciousness is released from its classical constraints. It enters a state of pure, uncollapsed potential, a state of superposition where memories, emotions, and possibilities can float and merge freely. Sleep is a nightly, voluntary retreat from the tyranny of the collapsed wave function, a journey back into the fertile, probabilistic sea from which all realities are born. The quantum world is not just a world of possibility, it is also a world of fundamental limits, a world where the very act of knowing changes what can be known. This is the essence of Werner Heisenberg's uncertainty principle, one of the most elegant, profound, and misunderstood concepts in all of science. It is not a statement about the clumsiness of our measuring instruments. It is a deep, intrinsic, and unavoidable feature of the wave-like nature of reality. The principle states that there are certain pairs of properties of a quantum system that are complementary the more precisely you know one, the less precisely you can know the other. The classic example is position and momentum. An object's momentum is a measure of its motion, its mass times its velocity. To have a well-defined momentum, a particle must have a well-defined wavelength, but a wave with a single, precise wavelength, like a pure musical note, is by its very nature spread out over all of space. It does not have a precise position. Conversely, to have a precise position, a particle's wave function must be squeezed into a very narrow spike. But a spike like this is a superposition of a huge number of different wavelengths, meaning its momentum is highly uncertain. You can know where it is, or you can know where it is going, but you can never, even in principle, know both with perfect precision. This is not a failure of our technology. It is a fundamental law of the cosmos. This principle has far-reaching consequences. It is the reason for the stability of atoms, preventing electrons from collapsing into the nucleus. It is the source of the zero-point energy of the vacuum, the irreducible quantum jiggle that ensures nothing can ever be truly at rest. And it is a powerful metaphor for the nature of our own consciousness and our search for knowledge. Our minds, too, operate under a kind of uncertainty principle. We can focus our attention with laser-like precision on a single detail, a single fact, a single aspect of a problem. But in doing so, we inevitably lose sight of the broader context, the interconnectedness, the bigger picture. Our knowledge of the position of the fact becomes precise, but our knowledge of its momentum, its meaning, and its relationship to the whole becomes uncertain. Conversely, we can adopt a broad, holistic perspective, seeing the interconnected patterns and the flow of the whole system. But in doing so, we lose the sharp focus on the individual details. There is a fundamental trade-off between focused analysis and holistic synthesis. As we prepare for sleep, we experience this mental uncertainty in a very direct way. The focused, goal-oriented mind of the waking state, with its constant attempts to control, to plan, and to know with certainty, begins to relax. We surrender to the gentle, associative flow of hypnagogic thought. The sharp boundaries between ideas blur. The distinction between memory and imagination fades. We enter a realm where knowledge is not about certainty, but about possibility. In the dream state, this uncertainty becomes the very fabric of reality. The world of the dream is not governed by the fixed laws of classical causality, but by the fluid, associative logic of the unconscious. It is a world where anything is possible, where the normal constraints of identity, time, and space are lifted. This is not a state of confusion. It is a state of profound creative freedom. It is in this state of uncertainty that the mind can make new connections, generate new insights, and heal old wounds. The uncertainty principle, then, is not a pessimistic limit on our knowledge, but a cosmic guarantee of freedom and creativity. It ensures that the universe and our own modes will never be fully predictable, fully controllable, fully known. It ensures that there will always be room for surprise, for novelty, for the emergence of the unexpected. And every night, as we surrender to the peaceful uncertainty of sleep, we are aligning ourselves with this fundamental, creative, and liberating principle of the cosmos. The strange and beautiful phenomenon of quantum entanglement is a direct and powerful testament to the holistic and non-local nature of the universe. It is a connection between two or more particles that is so intimate and profound that it defies our classical intuition about space, distance, and separateness. When particles are created or interact in a specific quantum mechanical way, their individual wave functions can become merged into a single, unified wave function that describes the entire system. From that moment on, they are no longer independent entities, but are two aspects of a single, indivisible whole, even if they are subsequently separated by vast cosmic distances. The classic example involves a pair of entangled photons. If they are created in such a way that their total spin is zero, then we know that if one photon is measured to have spin up, its partner, no matter how far away, must instantly be found to have spin down. The strangeness lies in the fact that, according to quantum mechanics, neither photon has a definite spin until it is measured. Each exists in a superposition of both spin up and spin down. It is only the act of measuring one that collapses the wave function of the entire entangled system, instantly determining the state of the other. This spooky action at a distance, as Einstein called it, seems to imply a form of communication that is faster than the speed of light, a violation of one of the most fundamental principles of physics. However, numerous experiments have confirmed that this is not the case. While the correlation between the measurement outcomes is instantaneous, it cannot be used to transmit information in a controllable way. The outcome of the first measurement is fundamentally random. You cannot decide in advance whether you will get spin up or spin down, and therefore you cannot use this to send a deliberate message. But the underlying, instantaneous connection is undeniably real. It tells us that our notion of a universe made up of separate, independent objects is an illusion, an approximation that works well in our macroscopic world, but breaks down at the fundamental level. At its core, the universe is not a collection of things. It is a network of relationships. This has profound philosophical and even spiritual implications. It suggests that the sense of separation we feel as individual beings is not the ultimate reality. We are all, in a very real physical sense, entangled with each other and with the cosmos as a whole. The atoms in our bodies were forged in the hearts of stars that died billions of years ago, their remnants scattered across the galaxy and eventually coalescing to form our sun, our planet, and ourselves. We are physically connected to the history of the universe, and perhaps, through the quantum nature of our own consciousness, we are also entangled in a more immediate, non-local way. The feeling of deep empathy, the sense of connection that can span vast distances, the collective consciousness that can emerge in groups, these are all experiences that hint at a reality beyond our individual, isolated selves. Sleep is a state where we may be particularly receptive to these entangled connections. As the ego, the fortress of our individual identity, lowers its drawbridge, our consciousness can become more open to the subtle, non-local currents of the universal quantum field. In dreams, our sense of a separate self often dissolves. We can merge with other people. We can experience events from a collective perspective. We can feel a deep sense of unity with the natural world. These are not just psychological fantasies. They may be the subjective experience of the fundamental, entangled nature of reality. They are moments when our individual wave function remembers its connection to the universal wave function. Entanglement is the universe's most profound secret, a secret that tells us that despite the vast, cold distances of space, nothing is truly separate. We are all part of a single, vast, and mysterious quantum dance, and in the quiet, boundaryless realm of sleep, we are invited to join in, to feel the rhythm of our own connection, and to remember the deep and beautiful truth of our own, inseparable unity. The thought experiment of Schrödinger's cat, with its absurd and paradoxical imagery, has become an enduring cultural touchstone, a symbol of the profound weirdness that lies at the heart of the quantum world. But its importance goes far beyond its role as a clever metaphor. It is a powerful conceptual tool that forces us to confront the deepest and most uncomfortable questions about the nature of reality. The cat in the box, suspended in its ghostly state between life and death, is a direct challenge to the philosophical position of naive realism. The common sense idea that the world is exactly as it appears, and that objects have definite properties whether we are looking at them or not. Quantum mechanics suggests that this is not the case. At the fundamental level, reality is a realm of potential, of probability, of superposition. The definite, classical world we experience is not the fundamental reality. It is a collapsed reality, a reality that has been actualized from a sea of possibilities through the act of interaction and measurement. This raises the question of where the cut between the quantum and classical worlds lies. At what point does a system stop behaving quantum mechanically and start behaving classically? Is it a matter of size, of complexity, of temperature, of interaction with the environment? This is the problem of decoherence, a central topic in modern quantum physics. Decoherence theory suggests that a quantum system, like our atom, rapidly loses its superpositional nature when it becomes entangled with its environment. The information about its superposition leaks out into the vast number of degrees of freedom of the surrounding world, the air molecules in the box, the photons of light, the cat itself, making it practically impossible to ever detect the superposition directly. In this view, The cat is never really both alive and dead. Its macroscopic nature means it is so strongly entangled with its environment that its wave function collapses into a definite state in an immeasurably short time, long before we ever open the box. The collapse is not caused by the conscious observer, but by the unavoidable process of environmental entanglement. This provides a pragmatic and physically plausible solution to the paradox, but it does not fully solve the measurement problem. It explains why we do not see macroscopic superpositions, but it does not explain which definite outcome is chosen from the initial superposition, or why. It pushes the mystery of the collapse from the act of measurement to the process of decoherence. But the fundamental question remains. This ongoing debate has a powerful resonance in our own search for self-understanding. Our own consciousness can be seen as a system that is constantly navigating the line between quantum-like potential and classical-like actuality. Our inner world is a realm of superposition of conflicting desires, of unresolved emotions, of potential life paths. This is the realm of the unconscious. Our waking, conscious mind, however, is a collapsing agent. It is constantly making choices, forming beliefs, creating a coherent narrative of who we are. It is collapsing the vast, superpositional potential of our psyche into a single, definite, classical self. But this classical self is always, to some extent, an illusion, a simplification. The underlying quantum potential is still there, and it often surfaces in our dreams, in our slips of the tongue, in our moments of creative insight. The process of psychotherapy, in many ways, is a process of consciously re-engaging with this uncollapsed superpositional aspect of ourselves. It is about opening the sealed boxes of our own past, of facing the inner Schrodinger's cats of our traumas and our disowned desires, and in doing so, allowing for a new, more integrated collapse to occur. Sleep is the natural, nightly laboratory for this kind of psychic work. It is a time when the classical, collapsing ego is put on hold, and the quantum, superpositional unconscious is allowed to come to the fore. In the bizarre symbolic language of our dreams, we are given a chance to dance with our own possibilities, to confront our own paradoxes, and to glimpse the deep, strange, and beautiful quantum reality that lies at the heart of our own being. The phenomenon of quantum tunneling, the ability of a particle to pass through a classically forbidden barrier, is a stunning testament to the wave-like nature of reality and the probabilistic heart of the universe. It is a process that is both deeply mysterious and utterly essential to our existence. The sun shines, our digital technologies function, and the very elements that make up our bodies were forged in the hearts of stars, all thanks to this strange quantum leap. But quantum tunneling is not just a physical process, it is a powerful metaphor for transformation, for breakthrough, for the emergence of the new and the unexpected. It tells us that the barriers we perceive in our own lives, whether they are physical, emotional, or psychological, are not as solid and absolute as they may seem. Our classical, logical mind often sees the world in terms of impenetrable walls. We do not have enough money, enough time, enough talent. We are too old, too young, too broken. These are the energy barriers of our own psyche. And if we approach them with a purely classical, particle-like mindset, we will simply bounce off of them, our limiting beliefs confirmed. But if we can learn to access our own inner wave nature, the story changes. The wave-like aspect of our consciousness, our creativity, our intuition, our capacity for associative thinking, our ability to see a problem from a completely new perspective is not stopped by barriers. It can, in a sense, leak through them. A solution to a problem that seemed impossible can suddenly appear in a flash of insight. A deeply ingrained emotional pattern can suddenly release its grip. A new path forward can open up where before there was only a solid wall. This is the experience of mental tunneling. And it is an experience that is most accessible to us when we are not trying too hard, when we are not in a focused, particle-like state of mind. It often happens in the shower, on a long walk in nature, in the midst of a creative activity, or, most profoundly, during sleep. Sleep is the ultimate incubator for quantum tunneling. As the conscious problem-solving mind rests, the unconscious is free to explore the vast, interconnected web of our neural networks. It can make connections, try out new combinations, and test out new pathways that are not constrained by the rules of logic. It can tunnel through the mental blocks and the emotional barriers that have kept us stuck. This is why we can often go to sleep with a seemingly intractable problem and wake up in the morning with a clear solution, or at least a new perspective. The unconscious has done the work for us, not by breaking down the wall, but by finding a way through it. The story of quantum tunneling is a message of profound hope and possibility. It is the universe's way of reminding us that we are not trapped by our current circumstances or our past conditioning. We are probabilistic, wave-like beings, with a built-in capacity for breakthrough and transformation. It is an invitation to trust in the creative intelligence of our own unconscious, to honor the wisdom of our own sleep, and to know that even when we are faced with what seems like an insurmountable wall, there is always a chance, however small, of a miracle. There is always a possibility of tunneling through to the other side. The principle of superposition is a declaration that reality, at its core, is a realm of radical multiplicity. The universe is not a single fixed story. It is a library containing an infinite number of possible stories, and our lived experience is just one volume that we have chosen to read. This is a concept that can be both exhilarating and overwhelming. It is exhilarating because it speaks to a universe of infinite creative potential. It is overwhelming because it challenges our deep-seated need for certainty, for a single, stable, and reliable reality. But this multiplicity is not just a feature of the subatomic world. It is a defining characteristic of our own human experience. We are not single, unified selves. We are a complex, dynamic, and often contradictory superposition of different identities, different desires, and different life narratives. The psychoanalyst Carl Jung spoke of the archetypes of the collective unconscious, the hero, the trickster, the wise old man, the great mother as fundamental patterns of human potential that exist within all of us. The psychologist Roberto Assagioli developed a model of the psyche called psychosynthesis, which sees the self as a symphony of different subpersonalities, each with its own voice, its own needs, and its own perspective. We are a committee, a cast of characters, an internal ecosystem. In our waking lives, we often identify with only one or two of these subpersonalities: the responsible adult, the ambitious professional, the dutiful parent. The other parts of ourselves, the playful child, the wild artist, the contemplative mystic, are often suppressed, judged, or ignored. They are relegated to the unconscious, the uncollapsed superposition of our own being. But they do not go away. They continue to exist as a latent potential, and they often make their presence known in our dreams. Sleep is the great theater of our inner multiplicity. In the dream state, the dominant, waking ego steps aside, and all the other characters in our inner drama are given a chance to take the stage. We can have a dream where we are a courageous hero, facing down a terrible monster, only to have another dream the same night where we are a helpless victim, fleeing in terror. We can dream of ourselves as a wise sage, dispensing profound advice, and then as a foolish trickster, playing pranks and causing chaos. These are not just random, meaningless images. They are the voice of our unlived lives, the expression of our uncollapsed potential. The dream is the psyche's way of maintaining its wholeness, of reminding us that we are more than just the limited, partial identity we present to the world. It is a nightly invitation to embrace our own inner diversity, to honor all the different parts of ourselves, even the ones we find difficult or shameful. The process of becoming a whole, integrated human being is not about choosing one true self and rejecting all the others. It is about becoming a wise and compassionate conductor of our own inner orchestra, a person who can allow all the different instruments to play their part in the beautiful, complex, and sometimes dissonant symphony of our own being. Superposition is not a problem to be solved. It is a gift to be celebrated. It is the source of our richness, our complexity, and our infinite capacity for growth and transformation. And every night, in the deep, multiplicitous world of our dreams, we are given the chance to remember and to reclaim this fundamental quantum truth of who we really are. The decay of a radioactive atom is a quantum event that is both profoundly simple and deeply mysterious. It is simple in that it is a binary process. The atom is either in its initial, unstable state, or it has decayed into a new, more stable state. It is mysterious in that the timing of this event is fundamentally, irreducibly random. This randomness at the heart of nature is a deep challenge to the classical, deterministic worldview, which held that if we knew the precise state of the universe at one moment, we could, in principle, predict its entire future. Quantum mechanics tells us that this is not possible. The universe has a built-in, intrinsic spontaneity, but this spontaneity is not just a feature of the physical world. It is also a powerful metaphor for the nature of change and transformation in our own lives. We often think of personal growth as a slow, linear, and cumulative process. We read the books, we do the work, we make the incremental changes, but very often, the most profound shifts in our lives do not happen this way. They happen in a moment, a sudden insight, a flash of intuition, a moment of grace, a peak experience. These are the decay events of the psyche. They are moments when a long-held, unstable emotional or cognitive structure suddenly collapses, and we are transformed into a new, more integrated state of being. These moments are often unpredictable. They can come in the midst of a deep crisis, or in a moment of quiet contemplation, but they are always transformative. And just as the decay of an atom releases energy, these moments of psychic decay release a tremendous amount of psychic energy, energy that was previously bound up in maintaining our old defensive structures. This is the energy of liberation, of joy, of creative flow. Sleep and dreams are a particularly fertile ground for these kinds of spontaneous transformations. The dream state is a realm of heightened emotional intensity and fluid, associative thinking. It is a state where the normal, linear, and logical constraints of the waking mind are relaxed. This can create the perfect conditions for a quantum leap in our understanding. A recurring nightmare, which represents a stuck, unstable emotional state, can suddenly transform into a dream of resolution and healing. A symbol that has been haunting our dreams for weeks can suddenly reveal its meaning in a flash of insight. We can wake up in the morning feeling fundamentally different, as if a great weight has been lifted, without being able to point to a specific logical cause. This is the magic of unconscious processing, the mind's own innate capacity for spontaneous self-healing and transformation. The law of radioactive decay is not a law of death. It is a law of change. It is the universe's way of ensuring that nothing stays stuck forever. It is a promise that even the most stable, rigid, and seemingly intractable patterns both in the physical world and in our own psyches, are ultimately subject to the possibility of a sudden, unpredictable, and liberating transformation. It is a reminder to trust in the spontaneous, creative intelligence of the universe and of our own deep selves, an intelligence that is always at work, both in the light of day and in the dark, mysterious and transformative crucible of our dreams. The wave-particle duality, the central paradox of the quantum world, is not a problem to be solved, but a deep, generative tension to be lived. It is the cosmic dance between the potential and the actual, the unmanifest and the manifest, the one and the many. This is a dance that is not just happening in the subatomic realm. It is happening at every level of our own being. Our lives are a constant oscillation between our wave-like nature and our particle-like nature. The wave is our connection to the infinite, the unformed, the realm of pure potential. It is our capacity for imagination, for intuition, for empathy, for a sense of unity with all of life. It is the part of us that dreams, that creates, that loves unconditionally. The particle is our connection to the finite, the formed, the realm of the actual. It is our capacity for focused action, for logical thought, for making distinctions, for navigating the practical world of time, space, and matter. It is the part of us that builds, that achieves, that creates a unique, individual life. A healthy, integrated life requires a dynamic balance between these two modes. If we live too much in the wave, we can become ungrounded, lost in fantasy, unable to bring our dreams and visions into the concrete reality of the world. If we live too much in the particle, we can become rigid, disconnected, cut off from the source of our own creativity and from our sense of connection to the larger whole. We become a thing in a world of things, a cog in a machine. The modern world, with its emphasis on productivity, on efficiency, on the quantifiable, on the individual, has a strong bias towards the particle nature of our being. We are encouraged to be focused, to be definite, to be certain. The wave-like aspects of our nature, our intuition, our creativity, our need for unstructured time, for connection, for simply being are often devalued, dismissed as impractical or unproductive. This creates a deep imbalance, both in our individual psyches and in our collective culture, and sleep is the great, nightly corrective to this imbalance. Sleep is the time when the particle-like ego dissolves and we are re-immersed in the deep, generative, wave-like ocean of the unconscious. It is a time for the other side of our nature to have its voice, to be seen, to be honored. In our dreams, we are not particles, but waves. We flow, we merge, we transform. The rigid categories of the waking world dissolve. The forgotten parts of ourselves are remembered. The connections we have lost are re-established. To sleep is to restore our wholeness, to rebalance the fundamental duality of our own being. It is to remember that we are not just the finite, separate, and mortal individuals we appear to be in the light of day. We are also, and just as truly, infinite, interconnected, and eternal waves in the vast, mysterious, and beautiful ocean of the cosmos. To understand the wave-particle duality is to understand the very rhythm of life, and to honor our sleep is to honor our sacred and essential place within that cosmic dance. The law of radioactive decay, with its inherent element of chance, offers a profound insight into the nature of time's arrow. We experience time as a relentless, unidirectional flow, a one-way street from the past to the future. The second law of thermodynamics provides the physical underpinning for this, stating that the overall entropy, or disorder of the universe, always increases. But quantum mechanics adds a crucial layer of subtlety to this picture. The decay of a single atom is an irreversible event. Once the atom has decayed, it cannot undecay. This process creates a distinction between the past and the future, a moment of irreversible change that contributes to the overall arrow of time. However, the timing of this event is not deterministic. The universe at its core seems to have a built-in element of spontaneity, of creative unpredictability. Time's arrow is not just the result of a slow, steady increase in disorder. It is also punctuated by these random, information-creating, quantum events. This suggests a picture of time that is not a smooth, featureless river, but a dynamic, unfolding process, a story that is being written, moment by moment, through the resolution of quantum possibility. This has a powerful parallel in our own subjective experience of time and personal growth. Our lives are not a smooth, predictable unfolding of a pre-written script. They are a series of moments, of choices, of decay events that shape our path, a sudden insight, a change of heart, a decision to leave a job or a relationship. These are the moments that define the arrow of our own personal time. They are moments of irreversible change, moments when the superposition of our own potential collapses into a single, definite path. And often, these moments are not the result of a long, logical deliberation. They can feel spontaneous, intuitive, almost random, a quantum leap of the soul. Sleep is a realm where we are particularly close to this creative, spontaneous nature of time. In the dream state, the mind is not bound by the linear, causal logic of the waking world. It can play with time. It can rehearse different potential futures. It can reprocess the decay events of the past. A dream can take a painful memory and reframe it, allowing for a new kind of decay, a decay of the old, painful emotional charge, and a transformation into a new, more integrated understanding. This is the healing power of dreams, their ability to work with the arrow of our own personal time, to help us let go of the past and to open up to the new possibilities of the future. The quantum nature of decay, then, is not just a curiosity of physics. It is a deep metaphor for the process of life itself. It tells us that the universe is not a static, predetermined machine, but a dynamic, creative, and constantly unfolding story. And we are not just passive observers of this story. We are active participants, co-creators of our own personal arrow of time, shaping our destiny, moment by moment, through the choices we make, the insights we have, and the deep, transformative work we do in the silent, timeless, and sacred space of our own sleep. The quantum principle of superposition, the idea that a particle can exist in multiple states at once, is not just a statement about the physical world. It is a profound revelation about the nature of the soul. Our classical, Western model of the self is that of a single, unified, and coherent entity. But our own direct experience, especially in moments of introspection and in our dreams, often tells a different story. We are a multiplicity, a chorus of different voices, a superposition of different selves. The confident self, the insecure self, the compassionate self, the angry self, the child, the elder. All of these and more coexist within the quantum field of our own psyche. This is not a sign of pathology. It is the very nature of our richness and complexity. In our waking lives, we often collapse this rich superposition into a single, socially acceptable persona. We present a single, coherent face to the world, but this is always a partial truth, a single collapsed state from an infinite sea of possibilities. The other selves, the other potentials, are not destroyed. They are simply relegated to the unconscious, where they continue to exist in a state of superposition. And it is in our sleep, in the theater of our dreams, that these other selves are given a voice, a stage, a chance to be seen and heard. A dream is a journey into the superposition of the soul. We can dream of ourselves as a powerful monarch, and in doing so we are touching the archetypal energy of the king or queen within us, our capacity for sovereignty, for responsibility, for just and wise leadership. We can dream of ourselves as a frightened, abandoned child, and in doing so, we are connecting with the vulnerable, wounded part of our own being that needs care and compassion. We can dream of ourselves as a wild animal, and in doing so we are accessing our own instinctual, untamed nature. These dream figures are not just random symbols. They are aspects of our own multiplicitous being. They are the other yous that make up the full superposition of who you are. To work with our dreams, to pay attention to them, to honor them, is to engage in a process of psychic integration. It is to become more aware of the different voices within our own internal chorus, and to learn to become a more compassionate and inclusive conductor of our own inner symphony. This is a process that leads to a greater sense of wholeness, of authenticity, of creative power. It is the process of moving from a collapsed, partial self to a more fluid, dynamic, and superpositional self. A self that can consciously embrace and integrate its own inner multiplicity. The quantum world tells us that reality is not a single, fixed thing, but a vibrant, multi-layered, and superpositional dance of possibility. And our own souls are no different. We are not single notes, but rich, complex chords. And our dreams are the music we make in the silent, sacred, and superpositional space of the night. The observer effect in quantum mechanics is a profound and unsettling revelation that blurs the line between the subjective and the objective, between the mind and the world. It tells us that the universe is not a detached, independent reality that we passively perceive. It is a participatory cosmos, a reality that responds to, and is shaped by, the very act of our observation. When we are not looking, a quantum system exists as a wave of potential. When we look, it collapses into a particle of actuality. Our gaze, our awareness, is not a neutral act. It is a creative world-shaping force. This is a concept that has deep and powerful implications for our own lives and our own power to shape our reality. The world we experience is not an objective out there. It is a mirror, reflecting back to us the quality of our own attention, the nature of our own consciousness. If we approach the world with a mindset of criticism, of judgment, of fear, we will tend to selectively perceive and amplify the evidence that confirms this worldview. The world will, in a sense, collapse into a state that matches our observation. The people we meet will seem more hostile. The challenges we face will seem more insurmountable. The beauty of the world will be obscured. If, on the other hand, we can cultivate a gaze of compassion, of curiosity, of appreciation, the world will respond in kind. We will start to notice the small acts of kindness, the hidden beauty in the everyday, the opportunities for connection and growth that were always there, but were previously unobserved. Our observation does not create the world out of nothing, but it does collapse the vast, superpositional potential of the world into a particular, experienced reality. We are the artists of our own perception, and this creative act of observation is not limited to our waking lives. Sleep is a time when the observer turns inward. The lens of our consciousness, which is usually directed at the external world, turns to face the vast, inner landscape of our own psyche. And in our dreams, we are both the artist and the canvas, the observer and the observed. The world of the dream is a direct and unfiltered manifestation of our own inner state. The characters we meet are projections of our own subpersonalities. The landscapes we traverse are maps of our own emotional terrain. The narratives that unfold are the stories of our own deepest conflicts and aspirations. And the way we interact with this dream world, the way we observe it from within, has a powerful effect on its evolution. If we run from the monster in our dream, it will likely grow larger and more terrifying. If we can find the courage to turn and face it, to ask it what it wants, it can often transform, revealing itself to be a source of hidden strength or a messenger of some forgotten truth. This is the observer effect at play in the laboratory of the soul. It is the recognition that our awareness is not a passive witness, but an active, transformative force. To become a more conscious dreamer, to bring a quality of lucid awareness to our sleep, is to practice this creative art of observation in its purest form. It is to learn to consciously and intentionally shape the reality of our own inner world. A skill that can then be brought back into the waking state. The observer effect is not just a strange quirk of physics, it is a sacred responsibility. It is a call to become more conscious of our own gaze, to recognize its power, and to learn to look at ourselves, at each other and at the world, with a quality of attention that is worthy of the beautiful, mysterious, and participatory cosmos we inhabit. The wave function, the central mathematical object of quantum mechanics, is more than just a tool for calculating probabilities. It is a poetic and powerful map of the hidden, potential nature of reality. It tells us that the universe, at its core, is not a world of solid, definite things, but a shimmering, vibrant sea of possibility. A particle is not a point, it is a wave of potential, spread out in space, containing the possibility of being found here, or there, or anywhere in between. The wave function is the mathematical description of this field of potential. It is the score for the cosmic symphony, a symphony where the notes are not fixed, but are a superposition of all possible tones, waiting to be played. This is a vision of reality that is deeply resonant with our own subjective experience of life. Our lives, too, are a wave function. Our future is not a single predetermined path, but a superposition of all possible futures. Every moment is a crossroads, a point where the wave function of our life can collapse into a new, definite state, setting us on a new trajectory. The thoughts, the feelings, the desires that flicker through our minds are the ripples on the surface of this deep, potential sea, the what-ifs, the daydreams, the imagined scenarios. These are not just idle fantasies, they are the exploration of our own personal wave function, the tracing of the different possible paths that our lives could take. And sleep is the time when we dive most deeply into this ocean of possibility. In the waking state, our consciousness is largely a collapsed wave function. We have made our choices. We are on our path. Our reality is, for the most part, definite and singular. But as we fall asleep, the collapse is undone. We decohere from the classical world and re-enter the quantum realm of pure potential. In our dreams, we are no longer bound by a single reality. We can experience a multitude of possibilities simultaneously. A dream is not a linear narrative. It is a holistic, superpositional experience, a cross-section of our own personal wave function. It can contain echoes of the past, premonitions of the future, and symbols of our deepest, timeless nature, all woven together in a single, multi-layered tapestry of meaning. To interpret a dream is to act as an observer, to collapse its rich, superpositional meaning into a single, conscious understanding. But the dream itself, in its raw, uninterpreted state, remains a pure expression of possibility. It is a reminder that our reality is not as fixed and solid as it appears. It is a reminder that we are always, at every moment, standing at the edge of an infinite sea of potential. The wave function is the universe's most beautiful and profound poem. It is a poem written in the language of mathematics, a poem that speaks of a reality that is not made of things, but of possibilities, not of certainties, but of dreams. And every night, as we close our eyes and surrender to the gentle wave-like currents of our own consciousness, we are given the chance to read a few more lines of this endless cosmic verse and to remember the deep, beautiful, and liberating truth of our own infinite potential. The universe, as described by modern physics, is a story of two grand and seemingly incompatible narratives. On the one hand, we have Einstein's theory of general relativity, the story of the large-scale cosmos, a world of smooth, curved spacetime, of galaxies and black holes, a world governed by the elegant deterministic laws of gravity. On the other hand, we have quantum mechanics, the story of the small-scale world, a world of discrete particles, of probabilistic jumps, of uncertainty and superposition. These two theories are the twin pillars of modern physics, and each has been confirmed with unprecedented accuracy in its own domain, but they do not seem to speak the same language. They are based on fundamentally different principles and mathematical formalisms. Finding a single, unified theory that can encompass both a theory of quantum gravity is the single greatest challenge in all of theoretical physics. It is the holy grail, the quest to find the single, underlying law that governs the entire cosmos, from the subatomic to the cosmological. This tension between the large and the small, the continuous and the discrete, the deterministic and the probabilistic, is not just a problem for physicists, it is a tension that we all live with, a fundamental duality of our own experience. We live in the macroscopic, classical world of our bodies, a world governed by the seemingly predictable laws of gravity and motion. But our minds, our consciousness, often seem to operate on a different logic, a logic that is more akin to the quantum world, a world of fluid associations, of nonlinear time, of superpositional states. Sleep is the realm where this tension between the two worlds is most acutely felt, and perhaps where a bridge between them can be found. As we fall asleep, our consciousness detaches from the classical, sensory world and enters a state that is deeply quantum-like. In our dreams, the normal laws of physics are suspended. We can fly, defying gravity. We can pass through walls, an act of macroscopic quantum tunneling. We can be in multiple places at once, a direct experience of superposition. The scale of our experience becomes fluid and dynamic. In one moment, we can feel as vast as a galaxy, our consciousness expanding to fill the cosmos. In the next, we can feel as small and insignificant as a single grain of dust. This constant shifting of scale, this effortless movement between the macro and the micro, is a hallmark of the dream state. It is as if our dreaming mind is a natural quantum gravity simulator, a place where the rigid distinctions between the large and the small dissolve, and a more unified, holistic reality is experienced. Could it be that the structure of our own consciousness is a clue to the structure of the universe? Could the way our minds bridge the gap between the concrete, physical world and the abstract, symbolic world of thought be a reflection of the way that nature bridges the gap between gravity and the quantum? This is a speculative but deeply compelling idea. It suggests that the answers to the deepest questions of physics may not just be found in particle accelerators or space telescopes, but also in the deep, introspective exploration of our own inner worlds. Sleep, in this view, is not just a biological function. It is a nightly journey to the very frontier of our understanding, a place where the two great warring narratives of the universe can meet, can dance, and can perhaps, in the symbolic, poetic language of our dreams, find a way to become one. The unresolved tension between gravity and the quantum is not just a problem for science. It is the central creative tension of our own human existence, a tension that we are invited to explore, to hold, and to integrate in the deep, mysterious, and unifying space of our own sleep. In the final analysis, the deepest mystery that the quantum world presents us with is not about particles or waves, but about ourselves. The journey into the heart of the atom has led us, unexpectedly, to the threshold of our own consciousness. The discovery that the observer is not a detached spectator, but an active participant in the creation of reality, has forced science to confront a question it has long sought to avoid: what is the nature of the observer? What is this thing we call consciousness that seems to hold such a privileged and powerful place in the cosmic drama? The classical, materialistic worldview, which has dominated science for centuries, sees consciousness as an epiphenomenon, a secondary and accidental byproduct of complex neural computation in the brain. It is a ghost in the machine, a strange and wonderful illusion, but ultimately not a fundamental aspect of reality. But the quantum world seems to hint at a different, more radical possibility. It suggests that consciousness may not be a late-coming accident in a dead, mechanical universe, but may be a fundamental, irreducible, and perhaps even primary aspect of the cosmos itself. This is the central tenet of a philosophical position known as panpsychism. The idea that consciousness, in some rudimentary form, is a property of all matter. In this view, an electron does not just have mass and charge. It also has a tiny, primitive flicker of subjective experience. As matter becomes more complex and organized, as in a living cell or a human brain, this rudimentary consciousness can combine and complexify, giving rise to the rich, multi-layered awareness that we experience. This is a staggering idea, one that completely inverts our normal understanding of the world. It suggests that the universe is not a collection of dead matter that somehow, miraculously, gives rise to consciousness. It suggests that the universe, from its very beginning, has been imbued with a potential for awareness, and that we, as conscious beings, are not a strange anomaly, but a natural and beautiful expression of this fundamental cosmic property. In this worldview, the quantum field is not just a field of energy and potential, it is also a field of nascent consciousness. The entire universe is a single, vast, and interconnected mind, and our individual consciousnesses are like eddies in this great cosmic stream. This is a vision that has been expressed in different forms by mystics and philosophers for millennia. The Brahman of the Vedanta, the mind of God of the Hermetic traditions, the anima mundi of the Platonists. These are all expressions of the same deep intuition that consciousness is the ultimate reality. What is new is that this ancient, spiritual intuition is now finding a tentative, but growing, resonance with the cutting edge of modern physics, the puzzles of the quantum world, the observer effect, entanglement. The nature of time may all be clues that are pointing us towards a new, post-materialist paradigm, a paradigm that recognizes the fundamental role of consciousness in the structure of reality. And sleep, once again, becomes our most intimate and direct portal to this deeper reality. As the conscious individual ego dissolves, we are given the chance to merge back into the universal field of consciousness from which we arose. The dream state, with its symbolic language, its non-local connections, and its creative power, may be a direct experience of the mind of the universe, expressing itself through the unique filter of our own personal history. To fall asleep is to remember our cosmic origins. It is to let go of the illusion of our own separateness and to reunite with the single, unified, and conscious field that is the source of all being. We are not just in the universe is in us. We are the universe's way of knowing itself, of feeling itself, of dreaming itself into existence. And the greatest secret of the quantum world may be a secret that we have known all along, in the deepest, most silent, and most sacred chambers of our own conscious hearts. The strange, paradoxical, and beautiful world of quantum mechanics is not a distant, abstract realm of interest only to physicists. It is the very ground of our being, the invisible, energetic, and conscious foundation upon which our entire reality is built. The principles of superposition, of uncertainty, of entanglement are not just descriptions of subatomic particles. They are deep, resonant metaphors for the nature of our own minds, our own lives, our own souls. The universe that the quantum revolution has revealed is not a dead and deterministic machine, but a living, breathing, and participatory cosmos. A universe that is constantly being co-created in the dance between potential and actuality, between the observer and the observed, and sleep, the state we enter every night, is our most profound and direct access to this quantum reality. It is a nightly pilgrimage to the source, a journey into the superpositional sea of our own consciousness, a surrender to the creative uncertainty of the void, an immersion in the entangled web of our own interconnectedness. To understand the quantum world is to understand ourselves in a new and deeper way. It is to recognize that we are not fixed, solid, and separate entities, but fluid, multi-layered, and deeply connected beings. It is to embrace the paradox of our own nature, to honor both the particle of our individual existence and the wave of our universal connection. It is to find a new kind of freedom, a freedom that comes not from control, but from surrender, a freedom that is born from the recognition that at the heart of reality lies not a rigid certainty, but an infinite, creative, and beautiful mystery. The journey into the quantum realm is a journey home, a journey back to the fundamental, magical, and dreamlike nature of our own true being. And every night, as we close our eyes and drift into the gentle quantum sea of sleep, we are given the chance to remember, to heal, and to be reborn